let's record this. All right, let's take a look at the next 2 weeks, see what we got, and then we'll look at review some acid bases. How's that look up there? Looks good enough. All right, so if we take a look, no zoom, no zoom, no zoom, no zoom. And today we want to finish equilibrium questions. I don't think we're gonna, we're a little bit behind on finishing this. No exam on next week because of Monday and Tuesday off. And let's take a look at what we got there. No zoom, no zoom, no zoom. I think we're gonna try to put a laboratory in. Problem is how many of you out there would usually be here today, and will you be here next Thursday or Friday? Is there anybody that should be in here right now? Okay, so that means that you two would do the laboratory and then be partnered up with people at home. It's a little bit nerve-wracking probably, but I think we'll be okay. So we want to perform that on next Thursday, which I believe is a black day or whatever. And then we will review the equilibrium unit, and Monday the test will go up to equilibrium. I think that's good. Questions about the next 2 weeks? Sweet. Let's take a look then. Today we want to look at back at acids and bases. And if you guys remember, this is again one of those units will probably be slower like equilibrium because we you know, some of you guys haven't covered it for a while, and others last year, if you did not follow along in March or whatever, then you may also have trouble. What is new device detector? All right. Not put page numbers on this. I'm getting mad at that. So if we take a look here, acids and bases, there are 3 major definitions. Back in the day, there's a man by the name of Arrhenius, and Arrhenius basically found that when you have something that's acidic, it donates a proton. All a proton is an H. You know, a hydrogen atom has a proton and an electron. So a hydrogen ion you can call that a proton because a hydrogen ion has lost an electron. So basically it donates an H+. A base donates a hydroxide ion in water. So this limited Arrhenius's definition to basically something that starts with an H, having an anion of some type, and then something having a cation of some type and having an OH. So that was Arrhenius's definition. There were other ideas in the time, but they didn't really hold true. For example, Lavoisier, if you remember, like the father of chemistry or whatnot, he thought that oxygen had something to do with acids and bases because compounds like H2SO4, HNO3, and if you remember, Lavoisier was always about the oxygen. That was one of the biggest things, and it didn't pan out. Again, Priestley came and kind of, you know, kicked him while he was down on this. Joseph Priestley had some ideas as well, and basically Priestley was just the scientist that always wanted to go against Lavoisier, but you know, that was the deal, so he kept him down on that. It wasn't until later that independently Bronsted and Lowry, using separate paths, I think it's like within the month, which is crazy. It doesn't sound like within the month, both of them put this idea up. And that sounds crazy now, like it doesn't sound like that big of a deal, but you have to remember this isn't where you can just submit something, electronically and stuff like that. You put your papers together and you actually had to, get them there. So this Bronsted-Lowry definition of acids and bases. Acid donates a proton, so an acid is a proton donor, and a base is a proton acceptor. And what makes this different is that all of these arrhenius acids are still those proton donors, or right? No big difference here. But the difference is this, is that now if we take a look, something like this that does not have hydroxide in it at all can react with H2O and become NH4 plus OH negative. So by accepting this proton from water, it was able to create still hydroxide. And we can take a look. Water itself does this as well. And I know, like, if this seems like I'm way, like, I'm trying to go all the way back on this because I know that some of you guys didn't pay attention to acid base maybe last year during the lockdown. So H2O plus H2O yields OH negative plus H3O. That's what's known as the self-ionization of water. So this water right here was a proton donor, making it an acid, and this water right here was a proton acceptor, making it a base. A substance that can do that is known as an amphoteric substance. Lewis definition, an acid is something that accepts an electron pair, and a base is something that donates an electron pair. Keep in mind, we're going to have coordinate covalent bonding in this. And basically, if you don't remember what that is, that's whenever both of the electrons come from one atom to form the bond. That's that coordinate covalent bonding. Is whenever you have a bond forming, usually it's one electron from each of the atoms involved in the bond. During a coordinate covalent bond, 2 electrons. That's why this is an electron pair donor. 2 electrons are coming to make the bond from one of the atoms. Now we know this has to be true if we have H plus, because it does not have any electrons, right? So H plus is an electron pair acceptor. It has no electrons, so something else that's going to bond with that H plus needs to bring those electrons into the particle. Well, let's say it's Cl minus, right? Cl minus has the number of electrons to actually donate to the H plus to make a bond between those. So there we have electron pair acceptor and electron pair donor. The acid will sometimes be referred to as an electrophile, which basically means that it's seeking electrons. And a base, a Lewis base would be called a nucleophile, which basically means it's looking for a nucleus to attack or attach to. This part right here talks about all of the hydrogen stuff. This would be a hydrogen in its atomic form. You can see that 1 electron. The difference here with hydrogen ion, it does not have that. So that 1s is completely empty. And that's why we would need electrons to be given to that hydrogen ion in order for it to actually bond. So the 1s orbital has the ability to hold 2 electrons since it's empty. The hydrogen ion has the ability to accept a pair of electrons to form a bond. And again, here's that term again. Remember, when one species donates the pair of electrons with the bond, we call that a coordinate covalent bond. If we look at both of these, ammonia and hydroxide, both of these have electron pairs that they can give. They're free to form those coordinate covalent bonds. One of the biggest ones that you'll see in if you look through old P reviews or something, old AP reviews or something like that, is BF3. So BF3, if you recall from our bonding unit in your previous chemistry class, B can get out of the octet rule by just having 3 bonds. So since that is sp2 hybridization, trigonal pyramidal, right? The shape here is trigonal pyramidal because we don't have that extra electron pair up here forcing it down or anything. We have sp2 hybridization. Well, just like the hydrogen here, look what we have here. We have that free hybridized orbital, which can accept 2 electrons. So here's a rundown of a very old AP question and the answer to it, but it's basically that what I've just given. It basically is just asking for the 3 ideas and the 3 theories, and then you can mark down the concepts behind them with some examples, and just as we did. And here is that BF3 example. If we take BF3 with the NH3, this is what we call a coordinate complex ion. Basically, the NH3 has given the electron pair to make a bond between these two, between the BF3 and the NH3. So that is a complex ion. That's not one that we are used to seeing, but if you are looking at old reviews and stuff like that, you will see that. So how does all this tie into the equilibrium? Well, we know that there are strong acids and strong bases. We have HCl, HI, HBr, HNO3, H2SO4, and HClO4. These are the strong acids. And what does it mean to be a strong acid? It means that you ionize completely. So hopefully at this point we know what ionize means. So if we look at the reaction here, HCl plus H2O yields H3O plus Cl negative. Notice I put a reversible reaction here. That's a little misleading. It's very hard for this reverse reaction to work with this because the K for this is very high, somewhere above 10 to the third. So if it's 10 to the third or higher, actually maybe I think they use 10 to the fourth. 10 to the fourth or higher, the reaction is going to essentially go to completion. And what does that mean? Well, that probably means the way you used to think about reactions before we did any of this reversibility stuff in equilibrium. You burn a piece of paper, all the paper burns, right? So a strong acid like these guys right here, their K is very high. So the forward reaction is much, much favored. Since the forward reaction is so favored, we say that it goes to completion. That means if you put this in here, you're not going to find a lot of this. You're going to find a lot of this stuff. Now, Scientists being scientists, they say, well, I don't want to call this the K sub EQ or the K of equilibrium. Let's call it the acid constant, right? So that's what they call the Ka or the acid constant, acid equilibrium constant. So acetic acid is always discussed as one of the weak acids. So if we take a look down here, we have a weak acid, again, reversible. We have H plus and A negative. You could have also done this with the H3O, the hydronium ion, and then the A negative. It's totally up to you if you want to put water in here. Why it's not done a lot is because water is liquid, which basically means that in the equilibrium reaction, I'm sorry, in the equilibrium equation, we would just replace it with 1. So if it is a weak acid, the Ka, you could have the H3O plus or H plus up there and the A negative over the HA. We don't bother again with the H2O because we're going to put 1 in there. For a weak acid, this is less than 1, right? And a lot of times, again, just as 10 to the 4th, it favors the forward reaction greatly. We call that going to completion, basically. If K is equal to a 10 to the negative 4th, then if we were talking about the solubility product constant, we would sit there and say that that is almost insoluble, right? Depending on how high K is, remember, going to completion, almost insoluble when you're looking at solubility. Right. So if your acid has a Ka that is way less than this, it's a very, very, very weak acid. The same can be said for bases. So if we take a look here, here we have something that is accepting a hydrogen ion. So this is a Bronsted-Lowry base. What that's going to do is that's going to accept the hydrogen ion or the proton, whatever you want to call it, from a water, making OH. If this does not do this very much, or again, we have a KB, much less than 1, then it would be considered a weak base. Your strong bases are your alkali metals and some of your alkaline earth metal bases. The rest are weak to some varying degree. Now KW, because water is so important, this is the self-ionization constant for water. So KW equals hydrogen ion concentration times the hydroxide ion concentration. Again, there's nothing down below it because water is a liquid. Now this actually equals 1 times 10 to the negative 14. So if you know the hydrogen ion concentration or the hydroxide ion concentration, you can find the other one. We take a look here. I can't remember the scientist's name, but there was a scientist, Soren Sorensen? Yeah, I'll have to look it up. But basically, he was tired of looking at all of these exponent type things. So basically, he would find what we call the P of stuff. And that is basically by taking the negative log, we can find the P of it. For example, if you want the pKa, you take the negative log of the constant for equilibrium for the acid or the base or whatever. pKw allows us to actually see, well, if we have this being part of it and this being part of it as well, and it's times 10 to the negative 14th, if we take the negative log of that, then we can change that so that we're talking about the pH and the POH. If you guys have done a lot of math with exponents, if we take a look at this, the pH plus the POH equals 14. If something is more alkaline, then it is closer to 14 if we're talking about something called the parts hydrogen. So you have the pH. If we're talking about the parts hydrogen, less than 7 is an acid. Greater than 7 is a base. If we're talking about the parts hydroxide, less than 7 is a base. Greater than 7 is an acid. Well, this scientist, who I can't remember right now, basically, this pH thing took off. And we use this today, right? To keep that in mind, this is huge. We use this today still. If you've ever done the pool, to balance out the pool, if you're swimming pool, or if you ever worked as a lifeguard or something like that, you might do that. They talk about hair products being pH balanced, everything. So that actual scale took off, and then the average person didn't have to deal with these crazy concentrations, dealing with hydrogen ion concentrations and hydroxide ion concentrations. They could just be given something like, lemon juice has a pH of 2. And what does that mean? Well, if you ask the average person, they're going to be like, that's acidic, right? Or at least know that, hopefully. Now, all of this comes together with basically what we call the four-corner diagram. Down in this corner, we have pH. So let's say you're given POH. Well, you use this formula right here to go from POH to pH. That formula would change to 14 minus POH equals pH. If you have pH and you want to do the hydrogen ion concentration, well, if this is the negative log of the hydrogen ion concentration, is parts hydrogen, then 10 to the negative of the pH, or what we would call the antilog of the negative pH, gets you the hydrogen ion concentration. If you have the hydrogen ion concentration and you want the hydroxide ion concentration, well, then you basically use that 1 times 10 to the negative 14th, or what we called the water equilibrium constant, and that would give you this one. Go back the other way, go back the other way, up, down, left, right. As it says on the AP examination, and that's something that you guys need to make sure that you need to make sure you show more of your work, because it doesn't matter which way you go as long as your work is shown. You can go through any, like if I wanted to get here and I'm over here, I can either go this way or this way. Yeah, makes sense because that's the way it is. Cool. So there is one further interesting thing about this, and I think that you guys may have seen it in the multiple choice questions on the whatever the check, focus check, or whatever they call it. And basically that is, if we have something like this, we have an acid and it yields the hydrogen ion concentration and the anion, that if it's weak, then that means that, you know, if it's very weak, that means that the forward reaction isn't really favored and the reverse reaction is. So if we have something in there that's going to, let's say, an ion like F, HF is a very weak acid. So if we have a fluoride ion in there, it's going to pick up stuff. And then as it picks these things up, that will change the actual reaction itself. So that F negative can act if HF is an acid, that F negative can act as a base. Now, this, if we recall, this is the acid, and this is what we call the conjugate base. If it's a weak acid here, you know, it's actually a stronger base than it is a weak acid. And that's based off of that equilibrium constant, right? Because if the forward reaction for this is very, you know, doesn't happen because of the Ka in this case, then the reverse of that will actually be stronger. And I think in one of the multiple choice questions, you actually had to deal with that where it was the F was actually picking out H's or something like that from the water, actually lowering the pH there. I'm sorry, raising the pH, lowering the increasing the hydroxide ion concentration and decreasing the hydrogen ion concentration. All right. Well, let us try one of these problems down here then. An example of a typical Ka problem would be as follows. Given the 0.50 molar solution of HA, calculate the pH of the solution. So again, what we're doing is we're dealing with those same ice tables. So we have our reaction. And we are starting with 0.5 molar. And then 0 and 0. And we have a 0.50 molar. So we're going to lose some of this and gain some of this. Luckily for us here, we're dealing with a 1 to 1 to 1. So it's going to be a 1 to 1 to 1. 0.50 molar minus X, X, and X. And then we need to make our Ka expression. Products on top. Reactants on bottom. And we know the Ka is 2.6. And the hydrogen ion concentration is X. The anion is X. And the Ha is 0.50 molar minus X. Now with this X, if we take a look, this is pretty small. We're above that -4 that we talked about, right? So again, we could do the quadratic equation with this. We could use the solver function on our calculator, or we can just ignore that. So what do we get? We get X squared over 0.50 equals 2.6 times 10 to the -5. I forgot my watch today. So we're going to take 2.6 times 10 to the -5, multiply it by 0.5, and then take the square root of that. All right? And we get 0.0036. And that equals the hydrogen ion concentration. And that equals the hydroxide ion concentration. Now, if you did pay good attention last year during this time, we actually had an equation that basically, how did we write it? The hydrogen ion concentration equals the square root of I believe we called it Ma times Ka. The molarity of the acid times the Ka, the acid equilibrium constant, and then the square root of it. So if you want to memorize a little formula versus doing a lot of this, this will work out for you quite a bit for an acid of that type. So I'm going to put some concentration things there so that you understand that it's the hydrogen ion concentration is equal to the square root of Maka. Now, one thing that we did is make an assumption here, since this was so low. So what we want to do is we want to do what's called the 5% rule. So 5% rule, 0.0036 is our concentration. We're going to divide that by the concentration of the acid and multiply that by 100. And if that's less than 5%, we're good. That means we don't have to do the quadratic equation stuff. And that will go on to your college because the AP said that they don't put anything that you have to do the quadratic equation in there for. But whenever you're in college, professors might. So we get 0.72%. That's well less than 5%. So we're good with that. No questions there. The last thing is that this problem is not done. This actually asks us to calculate the pH. So in order to calculate the pH equals the negative log of the hydrogen ion concentration. And in this case, that is the negative log of 0.0036. And again, I don't know my calculator watch. It's gonna be a terrible day because of that. Negative log of 0.0036. That gives us a pH of 2.443697. And we didn't deal with significant digits when dealing with log base. I don't know if your other teachers teach you significant digits at all, but this has two significant digits and this has two significant digits. And that's why that hydrogen ion concentration had two significant digits. If it's two significant digits, that will lead to two decimal places after taking the log. So two significant digits, two decimal places after the log. And that's why we always took pH out two places in the past, because usually we're dealing with KAs and stuff like that that have two significant digits. If we didn't teach it, we just rounded to two significant digits. Questions there? A recap of this. Again, this is the reasoning why we can drop that x through the subtraction. You can't do that through multiplication. Keep that in mind. And the 5% rule, we just taught that. Oh, and there's the two places plus the decimal. So the last 3 seconds of all of that. Please, I'll give you guys the rest of the class period to do this problem right here. It's very similar, except for you're using hypochlorous acid. Oh, I'm sorry, that's hypochlorite. Yeah, hypochlorite. Cool. Questions? All right, next week we want to try to get back to a little bit of normalcy and have a laboratory. Looks like it's going to be these guys doing it. So that'll be cool. Have a great weekend. If you have any questions, by all means, stay after. William, I did that thing that you asked me to do. It's done. They're updated. And what else? I have anything else to talk about? No, I don't think so. Cool. Take care. Stop the recording.